bit about logistics. I think that's probably a prudent discussion today. But first off, you all have a present for me. You have homework 5 due today. Let's do that. Let's go ahead and turn that in if you haven't already done so. Homework 6. I have yet to complete the assignment. I'll post that later today. As of right now, that'll be due Friday, March 16th. Not Friday, that's wrong. It's Friday, March 20th. Sorry about that. That's a typo. Oops. Friday, March 20th. Since we had originally decided to cancel class that day, which we are canceling in-person class on the 20th, as of right now, I'm going to have you turn that in on the cart outside my office. So just lay it on the cart. Everybody know where my office is. You know, second floor, last office on the left. Just throw the assignment on the cart. Assuming that our schedule remains unchanged, if you all turn that in by, say, class time by 10 a.m., that'll be fine. Is everybody okay with that? Keep turning in early, whatnot, I'll be fine with that. I think it would be prudent if we took a few minutes to talk about COVID-19 and some updates regarding that. So just so everybody's aware of this, the last 48 hours we've had some developments at our neighboring institutions, right? So we've had cancellations and whatnot in the state of Ohio, the state of Maryland. Last night at, I think, 10 p.m., WVU said that they were going to be canceling their classes for the foreseeable future after next week. So I think it stands to reason that we're next. Or if I was a betting man, it's not a matter of if, it's a matter of when. So I'd like to talk just about some logistics regarding the class and some things that we're probably going to have to do just to make sure that everybody gets everything done. So first off, let's go to the syllabus, because I think there's really 2 items up for question. And number 1 is course operation, and number 2 is your grade. So let's talk about the grade. So the grade in the course is based off the attendance, the homework, and the 3 exams. Okay? So one of the things you'll notice today is if you go onto Blackboard and you didn't have perfect attendance, your attendance grade is a little bit higher today than it was. What I've done and what I've decided to do for the rest of the semester is I'm just going to count everybody here. Okay? So I'm not going to take attendance for the rest of the semester. I'm doing that just because I don't want your grade to suffer as a result, but at the same time I don't want to deviate from the grading basis of the syllabus. So I figure a fair way of doing that is just say from here on out, everybody's here. So I'm not going to take attendance anymore for the rest of the semester. Everybody okay with that? That way, so from here on out, your attendance grade is 100. That doesn't mean I'm forgiving absences in the past, but I'm saying from here on out, everybody's here. Okay, let's talk about homework. I can still assign homework via Blackboard, and you all can still turn it in via Blackboard. I can set it up to where I post the assignment and you upload a document. You all can download have you all heard Cam Scanner or an app like that? So you can scan your homework in and turn it in that way. So we can do that. Okay. As for exams, we are still going to have exams in here. What I'll probably end up doing if we decide to go distance for the rest of the semester or something similar is what I'll do is I will set up an online exam, and so it'll be short answer. I'll probably, instead of making it a 1-hour time limit exam, I'll probably make it like a 2-hour time limit exam, given the fact that things are a little weird with the logistics, and have you all upload all of your scratch calcs and so on and so forth. Given the fact that if we have to do the exams at a distance, I mean, I can't prevent going on Blackboard and checking out the notes. I'll probably make them also open notice as well. Is that a fair assessment? Everybody okay with that? Okay. So in terms of the grade, I don't see the grade change, the way that we compute the grade changing. Like the only thing I think that was really up for debate is how do you count attendance if we're not here? And so I'll just count everybody here from here on out. So every day from here on out for the rest of the semester that we were scheduled to be here, I just counted everybody present. And so I uploaded that to Blackboard. So your attendance grade, if you didn't have 100% attendance, is higher than it was yesterday. Sound good? Okay. Now, the other item to discuss is course operation, which is, in other words, how do we have how do we have lecture if we're not meeting face to face? And so, to be honest, I haven't really totally decided how I want to do that, but it will probably be something along the lines of, like every Monday, Wednesday, and Friday at 10 o'clock, I might stream the class either through Blackboard Collaborate. I might do YouTube Live. Hell, I'd even debated just doing a Twitch stream or something and just doing that. It doesn't really matter, just as long as everybody can access the course. Assuming that I don't encounter many technological hiccups, I will still plan to do class Monday, Wednesday, Friday from 10 to 11. Just how we do it is, I don't know. And maybe I'm being overly cautious, maybe nothing happens, but I don't think that's the case. I think we'll probably end up having some sort of decision in the very near future. So I just wanted to let you know that I'm planning stuff out, and the last thing I'm going to do is disadvantage the folks in this room. Sound good? All right, are there any questions? Okay. All right, then let's get back to the wonderful world of concrete design. So last time what we were talking about was shear. We hadn't quite finished this example, but ultimately this is what we're going to plot, and this is going to become clear here in a little bit. So I'm going to do the math to come up with this plot very, very quickly, and then I want to talk about design. The analysis for shear capacity is really, really simple. It's very plug and chug. All you do is you compute VC, which is your shear strength provided by the bare concrete, which is 2 lambda BD squared of FC prime, and then you compute the capacity provided by your stirrups, by the steel, which is the area of your shear reinforcement, the yield stress of that shear reinforcement, and then D over S, which is the number of stirrups that cross a given crack region. And then don't forget for shear, phi is 0.75. There is no determination of phi, it is just always 0.75. Now what we had done last time was we looked at this example, and let me pull up the notes. Oh. It decides to load. So this is sort of what we had done last time. We looked at the beam and we decided that it was a simply supported beam with a uniformly distributed load, and so it turned into a structural analysis problem. Now our uniformly distributed load in this case is going to be 6.6 kips per foot because that's the factored load on the structure. The reactions ended up being 79.2 kips. And then we broke out some CE 312s in structural analysis to determine an equation for shear. I'm going to tell you right now, that is a skill you're going to need here, being able to determine equations for shear. We're going to need that. That's not going to be some academic exercise like it might have felt like last semester. We desperately need those expressions in order to lay out our stirrups. Now, that's the load, okay? And actually, let me break out this spreadsheet. We had also started to plot this on a spreadsheet, and while it loads, I'll go ahead and move forward. I'm going to sort of cut all of this off. I'm just going to do my work inside here. Now, what I knew that was going to happen. All right. What I'm now going to do is look at the shear capacity. Okay, so the first thing I'm going to do is I'm going to compute the capacity provided by the concrete. So VC is 2 lambda BWD square root of FC prime, which is 2. Now let's go back to the beam, make sure everybody remembers what's going on. Here was the beam. So we have a beam that's 12 inches wide, and then the effective depth is 24 inches. It's 4 KSI concrete, and we assumed it's normal weight. So if we got normal weight concrete, what is lambda? 1. And then this is 12 inches, this is 24 inches, and this is the square root of 4, right? No. Put in PSI, and you get out PSI. So I saw somebody, I said, this is the square root of 4, right? And I saw somebody shaking their head. Nope. Put in PSI, get out PSI. It's not 4, it's 4,000. So, plug and chug, and so what do we get as an answer here? Anybody have an answer? Good.
3035.8. PSI.
That?
Yes.
Wait, hold on. So it's 3035.8.
I forgot the 12. Sorry.
Hold on.
I got 36,429.
36,429.
Yeah.
Now, what are the units for the answer? Pounds. Because, yeah, you put in PSI and you get out PSI, but the PSI is multiplied by inches and inches. So it's PSI times square inches, so the inches cancel. So this is 36.43 kips. Okay? Now, for the VS, unfortunately, there's not one answer for VS. Remember, what's the expression to compute VS? VS is the AB times FYT times D over S. And so it's a function of S, which is our stirrup spacing. Now, if you recall from the example, let me pull this up. Okay, so here's the stirrup layout, and our S term changes as we go along the span. So in region 1, for instance, our stirrups are spaced at 4 inches. So S is 4 inches for our first region. For our second region, S is 8 inches. And for our third region, S is 10 inches. So we have different VS values for each of these 4 regions. Okay? So let's sort of work this out. So let's say for region 1. Okay? So S is 4 inches, D is 24 inches. Now FYT is 60 KSI. Now the big question also is, what is AB? Okay? Now does anybody remember AB? That's the area of your shear reinforcement. Now let's look at our beam. Let me close this. Let's look at our beam. Come on. Oh Lord. Computer's being slow today. Now here's our beam. Now we have number 3 stirrups utilized. Now I can tell you the area of a number 3 bar is 0.11 square inches. Okay, that's a lookup. All right. Now if the area of the number 3 bar is 0.11, what is the area in shear? What's the area of our shear reinforcement for this beam? 0.22. And how did you get that? Well, and you're doubling it because if I crack across this beam, I'm cutting through 2 bars. Okay? So for this problem, AB is 0.22. All right? And again, the reason why is because we have a stirrup like this. If we had a stirrup like that, AB would just be 0.11. Okay? So the shape of your stirrup affects what your AB calc is. That make sense? So AB is 0.22 square inches. So BS is AB FY D over S. All right, 24/4. And so what is VS? May I have an answer?
79.2.
79.2 kips. Okay, so therefore, VBN is VBC plus VBS, which is 0.75 times 36.43 kips plus 0.75 times 79.2 kips, which is what? And don't forget your phi value. So when you're computing this, really the things you got to watch out for is don't forget phi, and recognize that you have to add kips to kips. Like you can't add pounds and kips. You got to make sure the units are consistent. So, everybody have an answer on this one? Anybody?
86.7 kips.
Thank you. 86.7 kips. Do I have a second on that? Okay, so let's sort of draw ourselves a little table here on the board, and we'll replicate this on Excel here in a second. So we have what? 4 regions. Okay, so I'm talking about these regions right here, okay? Now, with region 1, our S value, we said was 4 inches, okay? Everybody with me on that? Now, based on that, what did we get for a PVN? That's kips. Remind me, what did we just get? 86.7? So 86.7. Now, here's the other thing I want to make sure that we're clear on, is the x coordinates. Now, what I mean by that is I propose that that is the capacity everywhere that the stirrup spacing is 4 inches. In other words, if I look at this as if it's one big coordinate system, something like that, then I propose that this value is only valid from x equals 0 to x equals 52. Is everybody okay with that? So, for example, region 2 has a stirrup spacing of 8 inches. Now, we haven't computed that value yet, but I propose that's going to be a valid answer from 52 inches to x equals what? What's the x coordinate right here? 84 inches. Okay, and so the next one is 10 inches. I'm going to get an answer, and it's going to be valid from 84 inches to what? 124. And lastly, what about region 4? So what's the stirrup spacing in region 4? I propose there is no stirrup spacing in region 4. And so if there is no stirrup spacing in region 4, I propose VS is 0. So what is phi VN? Well, it's whatever phi VC is, because there are no stirrups in that region. And that's going to be valid from, here, hold on, I know this is probably kind of tough to see for you folks over here. Is that better? So that's going to be valid from 124 inches all the way to 144. Now, to be clear, that's not the entire length of the beam. This beam is 24 feet long, and I'm only preparing my data up until 12 feet, right? So the beam's 24 foot long, and I'm only going halfway. But that doesn't matter because this beam is symmetric. You know, the loading is symmetric about the center line. So once you figured out what's going on up until the center line, you're good to go. Does that make sense? So let's go ahead and do the remaining regions. So help me out with this. So okay, so somebody help me out, all right? Who's got a calculator? Mr. Schwartz. Help me out. If S is 8 inches, tell me what VS is. Everybody see what we're doing? Instead of 0.22 times 60 times 24 over 4, times 24 over 8.
39.6.
39.6. Anybody second them on that? Okay. Now, with that value, tell me what phi v n is. So 0.75 times this plus 0.75 times that.
$57.02.
57.02. Do I have a second on that value? He's shaking his head yes. Okay. Since you're shaking your head yes, I want you to help me with the other one. So let's do S equals 10. Tell me what Bs is and then ultimately what phi Bn is. Start off with Bs. So 57. Yep.
VS is 31.68.
31.68. Do I have a second on the Vs? Okay. Now the VVN.
$51.08.
Say it again.
51.08.
51.08. Do I have a second on that?
Yeah.
Okay. And then our last one, the stirrup spacing doesn't matter because there is no stirrups in that region. So phi Bn is just phi Bc, which is what?
$27.32.
27.32. Do I have a second on that? All right, so this is 51.08. This is 27.32. Everybody good? Okay. Now, if you were a little fuzzy about that, we can always just do it in Excel. So, for example, I can go over here. So this was the Excel problem I was doing, right? So maybe I'll do a little calculation over here. So what is it? So we had what region? 1, 2, 3, 4. So we have 4, 8, 10. And so what did we get? VS. So this is those are the answers we got for BS, right? And then we have BC. BC is 2 times 1 times 12 times 24 times the square root of 4,000. But that's going to give me my answer in pounds. Need to divide that by 1,000 to get kips. Right? And so phi Vn is pretty much what we got, right? 87 or 86.7, 57.02, 51.08, 27.32. Everybody with me on that? Okay. Now, let's look at these regions. Okay? This is from x equals 0 to x equals 52 inches, right? This is from 52 inches to 84 inches. So far, so good? But the problem with that is if you look at my plot, does everybody see how my plot is in feet? So maybe what I ought to do is convert these to feet. So what is 52 inches in feet? Help me out.
624.
No, other way around.
4.3.
So 4.33 feet. Okay, so this is 4.33 feet to what? What's 84 divided by 12 is 7? 7 feet, and this is 7 feet to what? What's 124 over 12? Say again?
2.3.
And this is 10.33 feet to 12 feet. Is that a fair statement? So, let's look at a new plot. So, okay. So you're telling me from 0 to 52 or to 4.33 feet, the capacity is that? Is that what you're telling me? And then from that to that, the capacity is that. Then from 7 to, what is it? What was that, 124? The capacity is that. And then from that to 12, the capacity is that. Is that a fair assessment? So watch this. Let's take our plot. Let's add some data. X values, we'll add these. Y values, we'll add these. See what happened? So does that chart kind of make sense? So like from 0 to about 4 some feet, that's the capacity. And then as we go down, the capacity lowers. So everybody kind of see what I did there? So what I'm plotting is the capacity of the beam versus its loads. And you see the capacity is always higher than the loads, which is what we want. We want more capacity than the loads that we're subjecting the beam to. So that, if you want to know, that is how I got that plot I showed you earlier. Like, let me go to the announcements. If you remember, that's how I got that plot. I just plotted this on top of that. Does that make sense? Now, don't worry, I'm not going to make you do that on a homework or on an exam. What I am instead going to make you do is lay out the stirrups so this happens. Okay? So the one thing, there's a couple things I want you to keep in mind. The first thing is that as you get closer to the support, your stirrup spacing tends to get smaller. Like you might start off with 4-inch spacing, and then you go to 6-inch spacing, and then maybe go to 12-inch spacing or something like that. And 2, as long as your capacity or your stirrup spacings is sufficient to resist the load, you're good. Okay? Now, does everybody kind of get the idea? All right. Let me tell you how we do it, and then we're going to have a full-blown stirrup design start to finish here in a bit. So let's talk about the method. But first, any questions on what we've been doing so far? Okay. Let's talk about the method. Okay. So like I said, this is going to be a little unique. It's way different than moment design, but I find it's a lot more, I won't say a lot more fun, but it's definitely a little bit more interactive. Now, when you're designing for shear, the unknown is the stirrup spacing, right? Because you've got your beam, you know the loads that are on it, you know that the beam is being subjected to uniform distributed load, you know the size of the beam, and so ultimately you're trying to space out stirrups to resist that load. So let me show you what I got going here. So PVN equals PVC plus VBS, right? So look what I have here. If you're trying to figure out the spacing, what do you have? Well, the capacity's got to be greater than the load. The capacity is PVC plus VBS. I know what PVC is, and as for VS, it's AB times FY times D over S. So just take this equation and solve for S. It's that simple. So if you can understand that expression, you're rocking and rolling. And we're going to be using that expression in various forms in order to solve for required stirrup spacings across the span. So don't worry, I got a little procedure I'm going to show you here in a second. Now, let's talk about ACI. Okay? ACI states the following. Okay? Now, let's do a little bit of figuring here. Let's look at this. All right. So what do we got? So VBN, you would agree that VBN has to be greater than or equal to VU, right? That the capacity's got to be greater than or equal to the loads. So what is VBN? So VBN is VBC plus VBS is greater than or equal to VU. So it might stand to reason that, well, if this is my scenario, if VBC plus VBS is greater than or equal to VU, what if I have a region that doesn't have very much shear force on it? So much so that I actually don't need any stirrups. Like if I didn't provide any stirrups, let's say the concrete has enough capacity. Well, what ACI says is that's great, but you're still going to put stirrups there. In fact, ACI says any time that the shear is greater than 1/2 of VBC, you got to put stirrups in there. Even if you don't need them from a structural capacity standpoint. Remember what I said about shear, right? When an element fails in shear, it goes quick. So what ACI says is, I don't care if the concrete is strong enough by itself to hold up the load, you are still going to put stirrups in any region that VU is greater than 1/2 of VBC, anytime. And that'll become, and the way that we design that will become clear here in a little bit. But that's sort of the first point I would mention. Now, that's the first point. Here's the second point, and here's where things get a little strange. Now, let's go back to the beam that we just did. Okay, so the beam that we just did, here was the structure, right? We had a simply supported beam, and then let's call that X, let's call that Y, and let's say that we are subjected to some distributed load. Okay, what does the shear diagram look like? Okay, well, what does it do? It goes up, some reaction, whatever the reaction is, it goes down, then goes back up. Would you agree that this is the shear diagram for this structure? Would you agree with that? Now, if all I'm concerned with is 1/2 of the beam, since everything is symmetric, so let's only concern ourselves with this part of the beam. At what X coordinate is the shear the highest?
0.
X equals 0, right? So would everybody agree that at X equals 0 we have the highest shear? Okay? So VU max is VU at X equals 0. Okay? Now, that is true. What the code allows us to do for design purposes is it actually allows us instead to begin our design at what I'm going to call VU star, which is instead the shear at X equals D. Okay? In other words, we do not have to use the shear force right here to begin our design. We can actually use the shear force right at X equals D. The reason why the code allows us to do that is because whenever you look at this, and I don't want to say at a microscopic scale, but when you look at this in a much more local scale, I guess you could say, it sort of takes a little bit of while in the beam for that reaction to transfer to the beam as a shear force. Right there at that local region of the support, what happens is you sort of get these like concentrated force effects. Right there at the reaction, the beam doesn't really experience that as a shear. More or less it experiences it as a sort of like a squishing on the end of the beam. And so for it to actually be a truly shear force inside the beam, you have to go a little bit away from the support. So in most cases, we can begin the shear design at a distance D away from the support. That doesn't mean we don't put stirrups in this region, we certainly do. But we put stirrups over here using the shear force here, not the shear force there. Now, that doesn't mean that we do that in all cases. There are certain cases where we cannot do that in concrete design. One of the biggest ones is when you have monolithic construction. So you have, let's say, a beam and a column cast integrally. When that happens, you do have to use the shear right at the base of the support. One very common concrete detail that you'll see in commercial construction is the use of what's called a corbel. So if you go to like a parking garage or something like that, you will see a column with this little, like a nubbin sticking out of it. And the beam sits on top of this little nub sticking out of the column. That nub has a technical term, we call that a corbel, okay? Whenever you're designing the shear reinforcement for this corbel, you use the shear right there at the support, not D away. You also have to use the shear at the support whenever you have load applied to the bottom right there near the support. But in most typical loading scenarios, you can back that off and actually go D away from the support. Don't worry, I'll show you how to do that here in a little bit. Now, for the regions where the concrete alone can carry the capacity, in other words, the code says we have to put stirrups there, even though we don't need them from a structural capacity standpoint. What we would do is utilize the maximum spacing. So there are two maximum spacing values that we have to provide. One of them is just based off of maximum spacing limits to ensure that the stirrups provide the capacity we want them to. And so if you recall from an earlier lecture, there was actually two limits. I'm just going to use the first one since it's a little bit more stringent. Don't worry, I'll summarize a lot of these formulas for you later. So S max 1 is just going to be the minimum of either D over 2 or 24 inches. And then the second limit comes from our minimum steel reinforcement requirement. Remember, the code does say that we have a limit on how much steel we can provide. And I don't use that limit to solve for what's the required AB. Instead, I back calculate that and I say, okay, well, what stirrup spacing do I need to provide to meet that limit? And usually we can choose a stirrup at the beginning of the problem. We can say, let's say we're going to use number 3 U-shaped stirrup. So we know AB is 0.22. So in order to satisfy this limit, we just figure out what does S need to be. And so we get a maximum stirrup spacing. Okay, so here's the procedure for design. So if you're wanting to write stuff down, this would be the best place to start writing stuff down. So the first step that we have in shear design is to construct the shear diagram. And let me be clear, it's a little bit more involved than just doing this, okay? Because there's going to be regions in the shear diagram that we have to identify. Regions where the concrete alone carries the shear, regions where we don't need stirrups at all, but then obviously from a capacity standpoint, we need to know which section the stirrups are required. So there's actually going to be 3 separate regions that we identify in our reinforced concrete segment. So section 1, section 2, and section 3. The problem that we're going to do first, it's going to be pretty easy to solve for which region is which, because there's only going to be a single equation defining the shear diagram. But whenever you have point loads or concentrated loads on the specimen, it's not that this gets harder, it actually gets easier to determine mathematically, but it requires a bit more critical thinking. So you kind of have to look at the diagram and see what's going on. So, but like I said, we're going to have 3 regions, one where the stirrups are required, one where concrete carries the shear and where you would probably use S max, and then finally where you don't need any stirrups at all. Okay. Any questions? All right. That's procedure 1. That's okay. Now let's go on to step 2. The next thing that you do once you've got your shear diagram is you figure out your starting S value. And so your starting S value, you figure out the required stirrup spacing at a distance D away from the support. And so I'm calling that shear D away from the support, I'm calling that VU star. So that's the very, very first shear spacing that you provide. Excuse me. So using that equation I derived before, you solve for the required stirrup spacing. So phi AV FYD over VU star minus phi VC. That's a plug and chug expression. And then you just solve accordingly. Now, one of the things to keep in mind is that this is a mathematical equation. We're solving for S. So when you solve for S, you're going to get S is 4.32638739. You are not going to tell a contractor to use 4.362839, blah, 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 blah. Okay, now let's talk a bit about conservatism, because I want this to make sense. Let's say you're on step 2 and you solve the equation and you get S required is 4.32 inches. What are you going to use?
4-inch spacing.
4-inch spacing. You don't round up, you round down, okay? You round down because the capacity is a function of the stirrup spacing. As the stirrup spacing goes down, you're putting more stirrups in the beam, okay? So you don't round this up. You don't say, oh, the conservative value would be to round to S equals 5. No, that's unconservative. Round down, okay?
Even if it was like 4.8?
Well, that's a great question. So if it was 4.8, you could round down to 4. You could maybe round down to 4.5 if you wanted. But honestly, what happens in practice, usually people are specifying stirrups at like 2-inch increments. That's a very common value. So if I calculated 4.8, I'd go with 4. Because here's another point, and this will become clear when we start doing examples. The actual stirrup spacing that you use doesn't really matter. What matters is how many stirrups you put in the beam. So if you could use 4.5 spacing and you put 20 stirrups in the beam, but I use 4-inch spacing and I'm still putting in 20 stirrups in the beam, I'm going to use my spacing because it's not going to cost any more or less from a material standpoint, but my spacing is easier to figure out. Does that make sense? Is everybody else okay with that? Ultimately, the goal is to reduce the number of stirrups in the beam overall. And don't worry, when we start doing examples, this will become clear. Now, we can actually stop the problem right there. We're not going to get to a problem today. We'll start this on Friday, either online or in class. But to improve the design, we can also use the maximum spacing, because think, and if here's my shear diagram, in these regions of high shear, I might need to use like a 4-inch spacing, but regions down here, I could probably use like a 6, 8, 10, 12, whatever. But I'm going to be limited by my maximum spacing. So at the very least, I'm going to have my required spacing at the very beginning, and then my maximum spacing that I can utilize. So to improve the design, I want to use my maximum spacing as well. So to improve the design, we'll compute the maximum spacing, taking it as the smaller of one of these two, and then we'll start placing shear stirrups, okay? Once we get there, you'll see how we can possibly improve the design. And what I mean by improving the design is, let's say that my required spacing at the beginning is 4 inches, but let's say my maximum spacing is, I don't know, 10 inches. So at the very least, I know I'm going to have 2 regions. One where I'm using S as 4 inches, and one where I'm using a spacing of 10 inches. I might want to try and throw one in the middle. Maybe throw in, well, what happens if I throw in an S equals 6 inches? Maybe if I put a region in the middle, I can shave a couple stirrups off the beam. And you might think, oh, well, who cares if you've got one more stirrup in the beam? Yeah, but you might be using that beam 800 times in a given building. So getting that one beam optimally designed might be important if you're going to repeat that design over and over and over and over again. Does that make sense? All right. Lastly, we start spacing those out. You don't need to really so much go and verify a shear design as much as you have to maybe improve it with additional stirrup increments. But one last thing, you should check and make sure that your V sub S is less than this value. And the reason why is because if you go back a few slides, we were only adopting the most stringent maximum spacing, but that's if that's the case. Now I know that I'm throwing a lot of rules and procedures at you, and we haven't really done many examples. That's what our next lecture is going to focus on. I want to just show you the next 2 examples to give you kind of an idea of where this is headed. So we have, our first example is going to be this. This is a simply supported beam with a uniformly distributed load. And I'll go ahead and tell you, this is probably the easiest shear case that you'll have, is designing this. I'll go ahead and also tell you, one of your homework problems is going to be just like this. Okay? So this is easy. This, however, is a little bit more difficult. This is our next example. Because what those point loads do, if you remember when you start drawing your shear diagram, so here's your shear diagram, you jump up, over, bam, over, and so on and so forth. And so those interruptions in the shear diagram are going to make it a little bit more difficult to determine when you use these stirrup spacings or not. Because as you'll see when we get into example 13, we're going to rely pretty heavily on the equations to determine certain distances. And those equations will start to give really wonky answers on example 14. Okay? So we'll take our time with these two examples, and then that's really all there is for shear, and that's all there is for your second exam. Sound good? Okay. So for those of you that are not in steel, just do me a favor, keep your eye open for the news, pay attention to your emails. As things change, I'll be in touch. And for those of you in steel, I'll see you here in a couple minutes. That's all I got.